In this video, we're going to be reviewing Chapter 2, starting with significant zeros. Leading zeros are never significant, and trailing zeros may be significant if there is a decimal point present, but won't be significant if there is an absence of a decimal point. So for example, all these leading zeros are insignificant, but if we have 800, the trailing zeros are insignificant. If we have 800 with a decimal point, then the trailing zeros are significant. Moving on to measurement, you always must estimate one digit past that which you know. I look at this and I see between 2.6 and 2.7, so I can say it's 2.65, 2.64, 2.66. Any of those measurements will be valid. If I'm adding or subtracting and I have different levels of precision on my graduated cylinders, I must round according to my least precise measurement. So if I read the one on the right as being 23.9 milliliters and the one on the left as being 2.67 milliliters, and I need to add them, I will get mathematically 26.57 milliliters. But because I didn't know the hundredths place in my 23.9, I have to round to the nearest tenths. That is according to my least precise measurement. So I get 26.6 milliliters as what I can report. If we are multiplying or dividing, there's a different rule with sig figs. Let's say an ant travels this distance in this much time. They have different numbers of significant figures. I can take the speed as, let's call this 4.5 centimeters over 5.36 seconds, and that mathematically comes out to 0.840 centimeters per second, but I need to round this to 0.84 centimeters per second because my least precise measurement had two sig figs. That's the 4.5 centimeters. Moving on, we have precision and accuracy. Precision is all about how consistent the data is versus accuracy, which is how close the data comes to an accepted value. So if I look at student A, all these values are pretty close to one another, and the average of them is very close to the accepted value. So this has both precision and accuracy. Student B, this is a very wide range, and it's not especially accurate either because 186.8 is a bit off of your 185. Student C, 181.6 versus 185, that is definitely a mean that is well off of the accepted value. So this is low accuracy, though all the values are pretty close together, so we could say these values lead us to a great level of precision. Percent error is something that we use to quantify accuracy. And so if we look at the experimental value, which is what you get, minus the accepted value over the accepted value and multiply by 100%, we can analyze this for student C. Student C's experimental value, the mean comes out to 181.6. And what this gives us is a difference in the numerator of 3.4 degrees Celsius. When we divide by 185 degrees Celsius, we get 1.8%. Note that we round to 2 sig figs because the numerator as a difference gave us 2 sig figs. And when we divide 2 sig figs by 3, we have to round to 2 sig figs. 1.8% is our final number. Moving on to scientific notation, if we have 1030, that is going to be 1.03 times 10 to the third. 10 to the third, because if we move the decimal place over, it's 10 to the third that we're multiplying by putting the decimal point next to the 1. Similarly, if we have 0.012, we need to move the decimal point, but in the opposite direction, we're multiplying 1.2 times 10 to the negative second to get this value. Metric prefixes, learn them. Kilo, milli, centi, deca, all of these, learn them. And we can use them to convert among units using dimensional analysis. So if we're asked what number of kilometers is 105 centimeters, what we can do is say we have 105 centimeters, we're trying to get to kilometers, we're multiplying by some conversion factors. The first of which is that there are 100 centimeters in 1 meter. Note that I have centimeters to begin with, and I divide by centimeters, and that leaves us with a new unit of meters. But we don't want meters, we want kilometers. Therefore, we need to go further. So after canceling out the centimeters, we now say that there are 1,000 meters in 1 kilometer, and the meters cancel, thus giving us the final unit on the left of kilometers, which is what we want. And if we multiply the numerator, 105 times 1 times 1, over the denominator, which is 100 times 1,000, what this comes out to is 0.00105 kilometers, or 1.05 times 10 to the negative third kilometers. And that's all for this video. Hope it's been helpful. Feel free to leave any questions or comments in the comment section below, and thanks for watching.